So our speaker today is Lia Vaš, and her title, as you can see there, is The Graded Classification Conjecture Holds for Graphs with Disjoint Cycles. Please, Lia, go ahead.
Thank you so much for having me here. This is such a great pleasure. Thank you, Gisela and Willy. So I guess that we have to start with, with Roosbeck. So Roosbeck, Hazrat got into graded rings, and I guess my guess would be that his motivation comes from some of the algebras that we all love and which are naturally graded. So ergo the graded rings. So the conjecture itself, which I'm going to shorten with GCC, was formed around 2011 in Roosbeck's paper. I guess it was published 2013, if I'm not mistaken. So, you know, there is this usual gap between archive and, and publication dates. I don't know how we want to date the graded classification conjecture. Let me also...
Okay. Maths analysis paper is
So let me also state that I will be making some assumptions here. I'm assuming that we all know what is Leavitt path algebra, what is graph sister algebra, what is talented monoid, what is, you know, the usual package. So if you are not familiar with any of these things, maybe a suggestion, read some material, Leavitt path algebra book or something else. And then you can watch the recording of the meeting. So I'm going to briefly formulate the conjecture, although I'm guessing if we are here, we kind of have a guess what it says. So it's saying that two Leavitt path algebras or graph sister algebras are graded, are isomorphic as graded algebras exactly when they're Grothendieck groups considered with this extra action of the group of integers coming from the fact that these algebras are graded, and considered as pointed groups are isomorphic. So we're going to say something about pointed in a second, but let me just mention what I consider gamma to be. So pretty much gamma is the group of integers, but I want to use multiplicative notation and TS generator, not plus and zero, because this Grothendieck group is also a abelian group. So there is this other Z action. And so to avoid having the structure of like ZZ module, I'm using gamma so that we have a group ring Z gamma and the action of this Z gamma ring. So let's also say something about pointed. So these Grothendieck groups, if algebra is unital, are considered with order unit, which corresponds to the equivalence class corresponding to sum of all vertices. And if the algebras are not unital, then generating interval takes over that role. And a generating interval of the algebra corresponds to summons of all classes of sums of finitely many vertices. So when you consider your Grothendieck group with these elements, then we can say it's pointed. I will also mention that GCC recently has been referred to other statements kind of related to the Grothendieck group, but not necessarily saying what I had on the previous slide. So this statement, for example, on graded Morita equivalence, I'm going to use GCC only to the statement in its original formulation, the one from the previous slide. So then I guess that this conjecture, that this question that Roosbeck had, was interesting to many people. This is not exclusive lists. Maybe some people should have a circle and I'm not aware of that. And maybe some people are not on this photo have a circle as well. So a lot of people were looking at it and a lot made some progress on it. Let me quickly summarize the happenings. So Rusbech, in that an Allen paper, was looking at the class of graphs such that every path leads to either a rose or a cycle without exits or a sink. So these paths are like necks and these things are like heads, I guess. So the name that he gave to this class of graphs is polycephaly. So he was looking at finite polycephaly graphs. I always think of some dragon with many heads. And that's the class that he showed actually that GCC holds for. And then in 2014, Pereira and Enrique Pardo showed a weaker version of GCC for finite graphs without sources and sinks. And then again, some number of years later, 2020, Soren Eilers, Efren Ruiz, and Aidan Sims showed the GCC for its sister algebra version. Most of these proofs hold both for graph C-star and for Leavitt path algebra. So they were looking at the class of graphs called amplified graphs, which are graphs such that if a vertex emits, then it emits infinitely many. So if a vertex emits an edge, then it emits infinitely many to that range of that edge. And then around 2016, so this was a year or two after I got into graded rings myself, Rusbech and I were looking at both the involution and the grading and what kind of effect these things have on the Grothendieck group. And then pretty much we were showing the full and faithfulness of the Grothendieck functors. So this would be something stronger than the GCC. And that is why in our result, we have this field dependence, because you see in all these other results that I mentioned, pretty much it doesn't matter what kind of underlying field you have. And here we have that you should be working over some nice enough field, like, for example, complex numbers. So if you have that, then you have that GCC holds for a class of graphs that consist of row finite, such that every infinite paths end in a sink or a cycle without exits. And these sinks can be something they called infinite sinks in so far one and only book on Leavitt path algebra. So then we come to 2025, when Soren Eilers and Efren Ruiz updated their 2019 post of some paper. And I'm embarrassed to admit that I wasn't aware of the update. I was aware only of the 2019 version until after I submitted my archive post, the first version. So they are working with two classes of graphs that actually turn out to be subclasses of the class of graphs we are about to consider. Acyclic graphs with finitely many vertices, and what we are about to call two S&E graphs with finitely many vertices. So the class of graphs we are going to talk about today is with these joint cycles, such that it has finitely many cycles, sinks, and infinite emitters. It can have infinitely many vertices, but finitely many of those three elements. And then each infinite path ends in a cycle. So that's going to be the star of the show today. So let's talk about S and E, and let's talk about N, S, and E. So what is this N that we have here going on? So N is this number of cycles, sinks, and infinitemeters from that previous slide. And that corresponds exactly to the length of composition series of the graphs. Or algebras, or talented monoids, or Grothendieck groups. So one thing that is great about this composition series business is that it doesn't matter if you are looking at admissible pairs and you are looking at composition series in the graph sense, or you are looking at Leavitt path algebras or graph C-star algebras for that matter, and then you are looking at graded ideals, or you are looking at talented monoids and gamma order ideals, whatever, or you are looking at Grothendieck groups. Everything is equivalent, everything has the same composition length, so that's that N. So S and NE stands for sink and no exit. So sinks and no exits, pretty much they come from 2 of the 4 primary colors. And before we say a little bit more about these primary colors, let me just do a quick example. So here is a nice little graph. It has 1 cycle, 1 infinitemeter, and 1 sink, and that is 3. And that's exactly the length of composition series of this graph. So pretty much, you kind of count these elements, and that exactly give you the length of composition series. The only prerequisite pretty much that we are going to need is this business with porcupines and quotients. So let me also briefly summarize that. So in 2007, Mark Tomford realized the quotient of Leavitt path algebra with respect to graded ideal as Leavitt path algebra of a graph, and the name for that graph is quotient graph. And then he did something similar, realizing the graded ideal itself, but what he had is isomorphism without graded. So if his construction leads to hedgehog graph, and then if you make the spines of this hedgehog a little bit longer, then I start calling that porcupine. And then that's the graph that realizes the graded ideal by a graded isomorphism. Then you have the lengths of paths also preserved. So so porcupine quotient is kind of thing that unifies these two things. So if you have 2 admissible pairs, one is bigger than the other in some natural sense, you are doing like a quotient construction, but relative to the porcupine graph of this bigger admissible pair. And then you have this realization of this quotient of these two ideals. So let's just do a few examples, and the reason why I'm doing these quick examples is because I think that this porcupine quotient can help you do induction for some other things, not necessarily graded classification conjecture. So I really think that that this is the way how you can, make your complex, crazy graph a little bit more manageable if you are going from one of these colors to the other. So that's why I'm just going to briefly go over some of the porcupines and quotients. So there is this nice Toplitz graph. It has one non-trivial and proper hereditary set. And these are the paths that end at that sink. And then the porcupine in this case would have only one spine, and that spine pretty much corresponds to unrolling this cycle. And you see how every edge is labeled exactly with one of these paths. So that's the porcupine. So this has composition length 2 because we have one cycle and one sink. That's 2. And the first composition factor is this porcupine, and the second is this loop. So this example also illustrates why we need to work with infinitely many vertices, because porcupine, this is a nice little finite graph, right? And the porcupine has infinitely many vertices. So if you want to do any type of induction, you really have to face the infinitely many vertices here. Trust me, it would be much easier if we work with only finite. There is this other example, the graph that we had on one of the other slides with composition length 3. So the porcupine here, H is again the sink. The porcupine here is when you kind of split this infinite emitter and then unroll the cycle for each, right? So that's why we have infinitely many of these porcupine spines. So this would be that first composition factor. In the middle here, we have the true porcupine quotients. So far, we have seen just porcupines or quotients. And the only thing, you see H is H, the only thing that distinguishes these two are the types of breaking vertices. So, the porcupine quotient in this case is everything that ends at V, everything that ends at this V. So in this case, it would be pretty much this cycle unrolled. So this is that spine, and then the last factor is again the loop. Okay, so then we have this nice thing going on that I already kind of mentioned, that it doesn't matter if you are working with the ideals of the algebra or of talented monoid or of the other monoid or admissible pairs, everything is equivalent. This is the porcupine quotient. It represents this quotient as well as that quotient, so that's a very good thing. The 4 colors. So pretty much this is. I look at these coffinal graphs, and they're really the building blocks of everything. So let's just see what the 4 colors are and why these joint cycles are going to be presence of only 2. So a Leavitt path algebra is graded simple if and only if there are no non-trivial and proper admissible pairs, and we say that the graph is coffinal in that case. And coffinal graph is exactly one of these four types. The one with a sink, the one with a cycle without exits and then stuff going in, the one with extreme cycles, which is a cycle such that if you have something leaving, then it has to come back. And the terminal path, which would be infinite path, following the same definition of as the extreme cycle. If something is leaving, let's say that we are looking at this bottom bunch of arrows as your infinite path. So if something is leaving, it's coming back. So that's the 4th element, let's say the green. So a graph is SNE if every 2 admissible pairs such that their quotient is a coffinal graph are either with a sink or with a cycle without exits. So in other words, you have just 2 of 4 colors. So if a graph is SNE, then it's necessarily with disjoint cycles. Because if you have a cycle that is not disjoint with something else, it would give you an extreme cycle somewhere in that composition series. If you have finitely many vertices, then the converse holds. And this class of graphs that we are looking at, these 3 properties from one of the previous slides, that's exactly the class of graphs that are SNE and have finite composition series. The length of composition series is finite. So pretty much the requirement that the cycles are disjoint will give you no red. This other property about infinite paths will give you no green, so you have only blue and yellow. And the fact that you have finitely many cycle sinks and infinite emitters is giving you that you have finite composition series. So that's why these are equivalent. Some examples. So this first one is SNE, but not composition SNE. It is SNE because it has disjoint cycles, but there is infinitely many of them, so that's why it's not composition SNE. And certainly you can have a cyclic graph that is not SNE, and the reason why this one is not SNE is because this path here doesn't end in that sink, right? So this would be one of the composition factors. This is what they call infinite sink, right? Like an infinite path without bifurcations, pretty much. Okay, so the composition SNE is the class that we are into. And let's start with n is equal to 1, nice and easy. So since Rusbech's Allen paper, it is known that GCC holds for finite 1 SNE graphs because they are polycephaly. And these polycephaly graphs, they are all matricial algebras over some like field or Laurent polynomials or light path algebra of roses. So there is this nice matrix representation, and that was actually used in the approach towards polycephaly and their GCC status. So yes, there is this graded matrix representation, but that doesn't help us because when n is bigger than 2, then we don't have this graded matrix representation. So we don't want to consider that luxury that we have for a 1 SNE, so that we can do matrices, because we don't have matrices for n bigger than 1. Okay, so the general idea that we are going to have here is that we want a graph which represents, well, all graphs with algebras in the same graded isomorphism class. And we are going to also put star on that in front of that isomorphism, graded star isomorphism class, so that we will have that everything we say holds for graph C-star algebras as well. So this nice representative graph, I chose to call a canonical form. If that's the best name or not, I don't know. We will see. We can talk about that. And let's define this equivalence relation where two graphs are equivalent when there are canonical. Let's go back. When there are canonical forms that are isomorphic as graphs in the strongest sense, that pretty much you are just relabeling the names of like vertices and edges. So the main result that I would like to present today is that if you have a composition SNE graph C and F, then the following three conditions are equivalent, and 1 and 3 are your like GCC standard. But the second one is saying that two canonical forms of these two graphs are isomorphic. We will see that canonical form, how I define it, is not necessarily unique. So it's not saying that the canonical form is isomorphic of one graph with the one from the other one, but that you can find two canonical forms that are isomorphic. What we can also do is realize any isomorphism from condition number 1 by specific, in fact, graph operation, and then graded star isomorphism as well, which is also kind of nice that we know exactly how these pointed isomorphisms, how they look like. Timeline is something I have to address here because it's interesting to say the least. So March 2024, we are in Oberwolfach, and I'm saying these things about pretty much everything on the previous slide, this main result. I said, oh, you know, GCC and disjoint cycles and this and that. And then I added a bunch of stuff about Archimedes and sabbatical. But since nothing was out at the moment, this is pretty much how it came across. I realized that pretty soon after the talk. So I was very eager to go back to Philadelphia and finish the wretched thing and put it out. But little did I know what's going to be in store in Philadelphia. For me, it was everything that could have gone wrong, not in terms of math, but in terms of everything else. Pretty much went wrong, and fact that I was chairing the department and everything at university is changing, and there were millions of fires to be put out. That didn't help also. So I was pretty much not doing any math from March 24 to January 25. Then I went back to it finally. And it wasn't really, just a few weeks, like I indicated in Oberwolfach. It was 4 more months of work. But finally, then Wolf came out of its cave on May 22nd. So this day I will keep calling the day of the wolf. So now that's out of the way, we can go back to 1 SNE. Let's talk about some notation. So if you have one vertex emitting 3 edges to the other one, we are going to abbreviate that like this. And if you put that 3 in parentheses, that's going to stand for having 3 sources emitting each 1 edge to a vertex. This vertex here doesn't have to be a sink. It can emit a bunch of stuff, but these 3 are sources, and I call these edges, I call that tails. So, okay, so now that we have this notation with number in parentheses stands for these tails, now we can talk about 1 SNE canonical form, and we can see it because it has nice pictures with this abbreviation. So as it happens, this 1 SNE canonical form is going back to my 2020 Beitrage paper. It's a small, relatively short paper. I don't think that it was on anybody's radar. It wasn't even about GCC. It was about if you give me a matrix algebra, how do I know whether it is Leavitt path or something or not, as graded algebra. So, so you see, thinking about that question, I was trying to come up with graphs that would represent those matrix algebras, and these are pretty much the 1 SNE canonical forms. It's just that this paper was only about finite graphs, but you can easily do the countably infinite generalization. So, for example, if you have a graph that has a cycle of length m and some paths going in it, the rest of the graph is kind of nice and row finite, so that the graph is cofinal. Then the graded isomorphism class of such an algebra is uniquely determined by the length m of that cycle and by these numbers of paths of length 0, 1 up to m minus 1 modulo m. So if you want to find a graph that is going to be kind of uniquely determined in this case and nice enough and representable of the class, then you can pretty much attach these tails to these vertices in the cycle, and that's it, right? So for example, paths of length 1, there is mu 1 minus 1 of them, and there is one more here, so altogether mu 1 of them, so that's why, you know, it works. So this would be the the canonical form. I'm not saying that these canonical forms, the way how I look at them, are unique, or if somebody else comes up with something else that represents well, also that's, you know, totally possible. So other approaches can exist. Let's talk about the sink case. So if you have a graph with a sink, and let's say that everything else is row finite, then you have one path of length 0 and some number of paths of length 1 and 2 and so on. K in this case can be finite or infinite. And then you make you take this like line of length k, and I call that spine, and then k would be the spine length. And then you again attach tails pretty much based on these mu's here. And a short example here, if you have this graph here, it has two paths of length 1 and two paths of length 2 to the sink, and that would be the canonical form. We see the spine and we see the tails. So pretty much this is what you have for n is equal to 1. But before we go to higher n, let's do something like this, but relative to a set of vertices that you kind of don't want to mess with. So I call that relative canonical form. And the only reason why we really need that is because we would like to, for higher SNE graphs, in here we have two SNE graphs, we would like to make this path of length 2 that kind of connects the emitting cycle and the terminal cycle, we would like to have that path of length 1. So you are pretty much considering porcupine of this terminal cycle. So then there is more stuff down here. And your V is this set, this little v is in this example, your set capital V. And then your relative construction is going to be like mess with only this in between this connecting part. And you see this arrow here you can put there, and this arrow here you can put down here, so that the length from this little v to this vertex is kind of unchanged. So this is going to give us something that we will call direct exit to SNE graphs. Okay, and now since we are already talking about some messing with the graph in some sense, let's talk about these moves. Let's talk about, are they new? Are they moves? Can we call them moves? Are we violating some rules of symbolic dynamics if we call them moves? So I guess that another question that some of you may have is, if I want graded isomorphism to be preserved, is the only operation that I'm allowed to do the outsplit, because the other like classic moves, they are not preserving graded isomorphism. So I don't think that you can have just outsplits, because these two graphs, for example, I don't think that they are outsplit equivalent, and their Leavitt-Path algebras are certainly in the same graded isomorphism class. So so it's not just outsplits. Can we call these rearrangements? Can we call that moves? At first I thought no, and I don't call them moves in that archive post. I call them operations or transformations, because I don't want to, like, you know, mess with anything in symbolic dynamics or make her angry. And then I never publish again, because symbolic dynamics will curse me. So I don't call them moves. But when I was, I received some questions and comments from Rusbech and from Soren Eilers. I'm very grateful to them for these comments. They use moves, so I guess it's okay to call them moves. I don't know. What I want to emphasize is definitely they are not local, like some moves in symbolic dynamics, like the many classic moves, including some more recent ones like butterflies of Hawaii. They are local in a way because they do something to one finite portion of the graph. They changed it, right? But what we are doing here, we are changing stuff globally, right? We say, okay, some bijection exists, and let's just rearrange things based on that bijection. So you see, there is, for this is a quick example, this graph and this graph. The second one would be its like relative canonical form. There is nothing local about this move, right? So I'm not sure if we want to call them moves or something else, but we are definitely changing one graph into the other. Okay, now let's move to n is equal to 2. So the easy case is when you have either two sinks or infinite emitter and a cycle without exits, because when you have these two terminal things, everything else is row finite going to one or the other. And then you can do the out splits, and then the canonical form is just going to be disjoint union of two 1 S and E graphs. The algebra splits, the talented monoid splits, everything splits, so everything is super nice. There is nothing else that we need to say about this case. Two terminal clusters, easy peasy. So let's talk about the real thing, which is when you have only one terminal cluster. So in that case, you can have like cycle to cycle or cycle to sink or infinite emitter to cycle or infinite emitter to sink. So when I was like, deep in the middle of this, I'm thinking cycle to cycle, probably the hardest one. So let me just, figure that one out, and everything else is going to be like maybe easier or similar enough. Oh, little did I know that these four, let me tell you, these are four divas, and each diva has its own little quirks and, special things. So you have to kind of give them each attention, individual attention. So direct exits, we talked about this relative one canonical form. So if you have something to cycle, then you can make all the paths that connect that something, infinite emitter or non-terminal cycle, to the terminal cycle. You can make all these paths of length 1. So for example, here we have length 3 to this terminal vertex. And then you can make, using this relative construction, you can make all these paths of length 1. And then you are getting tails as a side effect here. So in this case, you're going to have infinitely many of them. I use omega because I want to emphasize that everything is countable. So you have countably infinitely many of these tails. And if you have blank to a sink, if you have two sink, then we have spine going on. And so you want all exits from your blank to be of length 1 before they hit the spine. So for example, here, this would be the spine. And here I have a path of length 2, and we don't want that. We want length 1. So we are going to take this one, put it here, and make this one into a tail. And we didn't change the number of paths or their length to the sink. So by that relative business, that's okay. So there is a lot of like screws to tighten. That's why I have this disjoint cycle here with Charlie on top tightening the screws. That's pretty much what's coming in the next few slides. Just tightening the screws. Okay, another thing that we want to do So if we have this type of thing like dangling from this sink here, we want to make that into neat tails. So this is pretty much something I call canonical tails. Make everything that can end in your terminal thing and not passing the non-terminal thing. Why is my screensaver? It keeps going on. So you want to make that nice and neat, and I call that making tails canonical, just another screw to tighten. Here we do have outsplits, right? Let's talk about them too. What do they do? So what you want to do is you want to make a first outsplit, total outsplit with respect to everything that is not in one of the terminal or non-terminal cycles or sinks, right? So when you have that, then you won't have something down from the quotient coming all the way to the terminal cycle, bypassing the non-terminal cycle or infinite emitter. So that pretty much means that if you are outsplitting anything, you are outsplitting with respect to something in the non-terminal cycle. So for example, if you outsplit with respect to this vertex, it's just two edges, so it's clear what the partition is. Then you have this, and when you make the exits being direct, then you have this. So you see there is this extra tail here now, right? So you see, in most cases, when you like move an exit, that's so going from here to here, I think of that as moving an exit. In this case, one full circle. So when you do that, when you move an exit, then you have some tails being produced. And so in most cases, you're thinking that moving an exit producing some number of tails. But you can certainly have something like this when you have infinitely many tails to start with. And then if you move this exit once, it will be up there. And if you move it again, then it will be again down here. Some tails are produced, but since there are already infinitely many of them there, the graph doesn't feel that. In other words, you end up with the same thing. So you cannot really say, well, canonical form is going to be something that is like it has the fewest number of tails, because you can certainly move exits and it's still the same number of tails. So you have to be mindful of that and think about both of these scenarios. But you can say that something is kind of reduced if if moving produces kind of more or the same. And you can also talk about reduced with respect to moving the exits like full circle in a way. So that's another thing that you have going on here when it comes to getting to that canonical form. And also something that I really wanted to do, because then on the Grothendieck level things are nicer and clearer, is to have single exit emitters. So in other words, I want only one of these vertices of a non-terminal cycle to emit exits. So for example, if this is your E, this would be, if you move this exit, it will go down there, and then this would be that single exit emitter for this graph. And then there will be a tail there. So the question of the day is, how are you going to decide when everything is maybe round and symmetrical and, both big wheels are turning, how you are going to decide which vertex to make a single exit emitter, kind of where to create those cycles that keep on turning to a halt. That's why I have Charlie here pushing on that brake. So if your non-terminal cycle has a vertex that either receives the longest path or receives the biggest number of paths, then it's clear where you are going to move those exits. So I call this such a vertex, such a special vertex. I call it feasible. And then you can move exits to a feasible vertex. But if your non-terminal cycle is such that there is really no way to tell U from V, or to tell them apart, then you say they're both feasible and you can move to wherever you want, and that will give you actually non-uniqueness of canonical form. I again want to emphasize that these canonical forms, this is just the way how I did it. It may not be the best way or the only way. Certainly it's not. So I'm giving you just my version. So if there is unique feasible vertex, like for example, for this graph, then this would be its unique canonical form. And if there are more feasible vertices, here, if you use this one, no matter where you move it, you will have an isomorphic graph, right? That's why if I changed the number of exits from this one here to make it more interesting. So if this is your E, then both of these are canonical forms of E and they are non-isomorphic. So now we kind of have enough of these operations in front of us that I think I can give you the idea of the proof. So let's say that we have these 4 graphs here. So the number of vertices here is relatively small, so that if you want to just compute everything, Grothendieck group, and say, okay, what if I have some f from one to the other? Can it exist or no? You can pretty much figure it out that like brute force way, that the algebras of all these 4 graphs are not isomorphic, graded isomorphic with each other. But if you do it that way, then there is no way for you to see if you have 50 vertices, graphs with 50 vertices and who knows how many edges and cycles and stuff, how you would approach that. So this is why I wanted to have single exit emitters. So let's see, if you take this 3rd graph and if you move this exit down there, this would be your single exit emitter form. And if you move this one, then it will go like this, and this would be your single exit emitter form. So now when you are comparing the 1st and the canonical form of the 3rd, now you immediately see that there cannot be lowercase f, the pointed isomorphism of the Grothendieck groups, because that order unit will not be preserved because there is this one more tail there. And same for these 2, right? So then you know that the 1st and the 3rd and the 2nd and the 4th, their algebras are not graded isomorphic with each other. So the number of tails is really becomes super relevant here. And if you were to compare the first 2, they are both single exit emitters, but the ranges of those exits are different. So you can say that exits are of different type. And that's why these 2 are not, don't have algebras in the same graded isomorphism class, and the same argument you can make for these 2. So pretty much this is how you can determine a graded isomorphism class. You convert to canonical form, and then you count the tails, and then you can tell whether 2 graphs have algebras in the same or not in the same graded isomorphism class. There is still one operation. Let me see how I'm doing with times. Okay, so there is still one operation. I will just say I'm going to rush because I see I'm out of time already. There is one more operation. This is relevant only for graphs with infinitely many vertices. I call it tail cutting, but I'm just going to skip it. I also want to mention something more about the realizing part. Let's maybe keep that for some other occasion then. Let's get to that n bigger than 2 finally. This is where the brass band is in full swing and those big wheel keep on turning now. So this is the composition series. You can make all these breaking vertices be empty. by outsplits. So for example, here we have a breaking vertex for this H here. And if you do outsplit, now you don't have breaking vertices anymore. So that's how you want to have all these breaking vertices in the composition series empty sets. And then it's the same spine and the same direct exits and the same thing. It's just that you need to be careful spine from where to where and direct exits from which cycle to which other cycle. So for example, if you're talking about the spines, then you are going to put these subscripts here. This is my H1, this would be H2, and the whole thing is H3. So if you are doing 2-1 spine, then you are thinking from here to there, and there is just one exit ends already there. So your spine is 0. And this would be your spine of length 1 for 3, 2, 1, right? And then you can have something like this with 2, 1 is 1 and 3, 1 is 0. You can have things like that. So all this tail cutting and canonical quotient that we didn't even have time to talk about are kind of analogous. Somewhere you have to, do some extra work for n bigger than 2, but then you can get the full result. Let me just go over super short summary of the proof. So you want to use induction for this E over H1. H1 and G1 are the ones that are really, really terminal. And then when you are rearranging the rest, then you first address H2 to H1, and then H3 to H1, and then rearranging that can mess only with Hj to H1 for J higher than 2. That's why you have to do it in that order, because H2 to H1 can mess some H5 to H1, but you will address it when you get there, and you are getting there in this order. And then you still have to look at the Grothendieck data and direct exits and single exit emitters and things like that. But you will see it works really, really well once when you have that n is equal to 2. So that's why this section on the n bigger than 2 has like only 20 pages in comparison to 40 for n is equal to 2. Some corollaries here. One of the questions, let me jump to number 3. One of the questions that I received after version 1 on arXiv was whether these operations that I'm doing preserve the diagonal. And then I was thinking about it, and the answer is yes. So that is now in version 2. If you are familiar with Soren and Efren 3-bit codification, the cube and 0, 1, 1, zeros and ones in all sorts of ways that match the vertices of the cube, this is the strongest relation. It leads to 1, 1, 1 in their codification, 1, 1, 1 relation. And the GCC is also related to another conjecture called a graded isomorphism conjecture. This is saying that 2 algebras are isomorphic as graded algebras if and only if they are isomorphic as graded rings. That would be graded isomorphism conjecture. Without graded, it would be same thing with regular isomorphism. So our 3 conditions from our main result are equivalent with all these other ones here. A diagonal preserving star can be in the sentence, or they don't have to be in a sentence, in all sorts of combinations. So pretty much these 3 holds if and only if the algebras are graded isomorphic as algebras, if and only if as rings, if and only if graph C stars are isomorphic. So final slide. I know, I'm sorry, I'm out of time. Final slide. What can we do? Where can we go from here? So I think that everything I told you pretty much holds for non-countable graphs. And I think that you can do some type of transfinite induction instead of regular induction. And I think this would work fine. I just didn't have energy to do transfinite induction after all was said and done. So, but that, I think it's true. And but more importantly, let's talk about a GCC for all finite graphs. So if, or not just finite, for all graphs with finitely many vertices. So if you have a graph with finitely many vertices, then you cannot have green. You cannot have that infinite path because it contains infinitely many vertices. So you have pretty much sinks, no exits, and extreme cycles. And I think that if we can find the answer for extreme cycles, then you can use these, like the way how the elements are connected, direct exits, things like that, to get to all graphs with finitely many vertices. But it's not just saying, oh, okay, so just extreme cycles, because extreme cycles, that's a quirky class of things, right? Because if you think about it, Kim and Rush example, these are extreme cycles, so it's not like, oh yeah, just show for cofinite graphs with the extreme cycles, and then that's it. It's a loaded question. But on the other hand, you can deal maybe just with extreme cycles, and then somehow that can lead to all graphs with finitely many vertices. So archive link is both in the abstract and the announcement. There will be V3, I think, at some point, because I received another question with some definition a little bit off. So there will be V3 at some point. And this is also an invitation for all of you to share your comments and thoughts, please.
So does your last word, your last sentence mean you have?
Yes.
Come to the end of your talk?
My talk ends with the invitation for.
Okay. So thank you very much for your talk. I have here a message from Ruhbe. He says to thank you on his behalf. He needed to leave because he needed to wake up early.
Yeah, I understand. I would totally understand if he's just watching the recording instead of being up in the middle of the night to.
Yeah, I'm sure he will watch the recording. I have one meta question. So, as in Oberwolfach, today you mentioned, this Jordan-Helder type of decomposition, and said that as a strategy, one should first try and prove the conjecture for all the slices, right? Yeah, but that already in that occasion and after today, I still don't see a clear strategy, even if we had the result for all the slices, how to put them together to get
it's not easy. It's not easy by all means.
But do you have do you have a germ of an idea of how to do this? Well,
so that's why there is so many Charlie Chaplins. Charlie Chaplins are pretty much putting it together. I mean, it's not definitely it's not easy how to put these things together. Mm-hmm. But if you do make it direct exit, that would be exactly one of the main strategies to make to connect these two things by only edges, right? Not not like paths of length more than one that can intertwine and that can do all sorts of things, but just single edges for one thing to the other. That would be, for example, one of the main steps that you need to take. So there is not like a straight answer, this is what you do and that's it. And it also depends on what kind of elements you have. You see, if you have only sinks and no exits, it may be easier than how you are about to do it if it has extreme cycles that are not just roses, but that may have vertices on all sorts of places. So it would still be a lot of work, and pretty much all these moves, including the tail cutting that I didn't have time to get to. And if you want n is bigger than 2, then it's also relevant how you make that quotient in a way canonical. So all these things lead to how you are going to connect the elements. So it's not easy by no means, but it does give you like something that is better than having just a bunch of these things and connected on all sorts of ways.
Okay, so are there questions from the audience? I saw a message in the chat by Enrique Pardo who saying he thanking you for the token, so he had to leave.
Okay,
but
no
apart
problem.
from that, I didn't see any questions in the chat. Nobody is raising their hand, so I will stop the recording here.